Like for example, both E1 and E2, you have reaction which you already have learned somewhere in your earlier classes, especially E2 mechanism you have done as compared to E1. Okay, so even if you just remember how is the reaction goes, that is more than sufficient. E2 is the one which has more importance. Now, as we have seen yesterday, elimination reactions means we are more interested towards dehydrohalogenations, removal of hydrogen, removal of halogen. So we get a unsaturated or a double bonded system. So if in this both the reactions you can see hydrogen bromine or hydrogen chlorine is being removed, we use a base like uh, potassium tetrabutaoxide or sodium ethoxide. We get an alkene hydrogen halogen from cases from saturated system we are getting unsaturated carbons. Okay. So this part uh, we had seen yesterday. Now, in all the cases, remember we need to have a base to do this job, okay, especially for dehydrohalogenation. Removal, D means removal, hydrogen removal, halogen removal. Now, let us look more detail. Even though you don't have even reaction mechanism, I will give you a very brief input. You can just look how it works. We are looking at bimolecular elimination, unimolecular elimination. So you already know what is bimolecular, unimolecular, where it depends on substrate along with the next additional species what you are going to add. Now, what is the difference between E2 and E1? It only differs in the timing of bond cleave. So how the bond cleaves, that is the difference, and how the bond is formed. So remember all of you, there is bond breaking and bond forming happening, which is same like SN1, SN2 mechanisms. Okay. Now, obviously E2, SN2 they will have common similarities, and E1, SN1 will have common similarities. What are the similarities? Till the carbocation formation, it is same step. Okay, because of carbocation forms. Once the carbocation forms, whether it eliminates or whether it substitutes, that modification we can see between E2 and SN2 or E1 and SN1. So you can see here, if it is a saturated carbon where you want to remove hydrogen and halogen, okay, we get a double bonded system, and we employ base, sodium hydroxide, ethoxides, and so on. What happens? This base will remove the beta carbon atom, proton especially. It base will it it is very much looking forwards for a proton. That too, a beta carbon. From the beta carbon atom, we will be having a proton, and along with that halogen. If base goes no, we'll have already one H plus there also. That will react with the halogen to get hydrogen halide or potassium halides or whatever. So these are called as yesterday only we have seen, like beta elimination reactions. Okay, so whichever is halogen is bonded to the carbon center, you call it as alpha, or it can be any substitution reaction, any substituted product. And the next adjacent carbon where it is attached to a hydrogen, it is termed as beta. So now base will take care of this, and the potassium salt or sodium salt will be taking care of this, so that we get beta elimination reaction. So this is gone, this is gone, hydrogen and bromine, so we get the double bond. Now let us see carefully what is happening for E2 mechanism. So this is the most commonly used mechanism or widely used mechanism for dehydrohalogenation, okay, like E2 mechanism. It generally shows second order kinetics. You already know, because when you have number 2, you need bimolecular. So where whenever you hear second order kinetics, it means that the rate depends on alkyl halide and base. They appear in the rate equation. So rate equation, you use both alkyl halide and the base. Now bond breaking, bond forming, or for example, how it will be done, we'll see it very shortly. So all these things happen like SN2 in a same step, in a single step, like a transition state. Now, generally E2 reaction, same like SN2 reaction, will use a strong base. That base should be strong enough to remove weakly acidic hydrogen, that is like beta hydrogen. Whenever you now you have a halogen here, this is a beta hydrogen, which is slightly be taken care by the strong base, and then you have the bromine which is leaving out, forming a double bonded system. Okay, this is for I'm just showing you one dimethyl substituted. If you have 3 methyl groups, you cannot see any E2 reaction. Okay, that is the reason you can see always a competition happening, whether I want to go for elimination or I should go for substitution. Okay, we will see that how it happens very shortly. So same like SN2 kind of mechanisms, we see compared to reactants, products will have lower energies versus reaction coordinates, how it happens, reactants to products. In the transition state, you see the development of partial charges with bromine and here, and as soon as the nucleophile attacks here, and bromine is ready to depart. So departing of bromine and departing of water. So finally you end up getting this kind of system. Okay? So here it is not like carbocation has formed, then it is looking for a base to react. All happens in transition in the same state. Like there is no two step, it's only one step. What happens means the CH bond, CBr bonds, CH and CBr bonds are partially of different carbon atom, are partially broken, and then you are and pi bonds are partially formed. So whenever these are broken, you see a pi bond formation. And what happens? Good leaving groups, and then you get a pi bonded or a double bonded system. So let us take one more example of the same isobutyl bromide. What we have seen now, we'll discuss more elaborately. Let us take potassium ethoxide. Okay, this is also a good base, strong base. Take this and react with isobutyl bromide. Again, for the people who are newcomers, the bonds in the dark ones represent which are facing towards you, and the broken lines correspond to the bonds which are away from you. When you bring this system towards this, you see, of course, the electron density will be more towards the bromine, so it moves. So this becomes slightly positive, and then this the positive part or the ethoxide part will be adding towards this carbon center, and then I mean adding means the whatever carbon, which is carbon positive charge is there, it tries to take away from the proton from the potassium ethoxide, and then it forms corresponding like ethanol, and then what we get is isobutylene. So this is the end product what we usually get. So the end product is isobutylene along with potassium bromide as the end products with ethanol. So this is how we observe SN like U2 kind of reactions. So very important stage is how both nucleophile and the leaving groups, same like SN2, they are in transition state. Okay, and then the reaction proceeds towards elimination reactions. Now, you already know it is second order reaction. Of course, there are a lot of parallels with respect to E2 and SN2, especially with respect to base and leaving group. So there also SN2 also, you know, base is a very important strong base, and how fast is the leaving group, halogen or like that, so that other can attack, and solvent effect. Okay, so this all plays an important role, like same like SN2, E2 also. In the case of E2 reaction, base also appears in the rate equation, same like SN2. So whenever base concentration increases, the reaction product will also increase. Okay. And also strength of the base will also affects the rate of the reaction. And strength means, like if you take 0.1 molar as compared to 1 molar reactivity will be faster. And E2 reactions, they are generally run with strong bases. You already know ethoxide, alkoxides. So you can see how SN2 E2 mechanisms, how they differ is how the R group affects the rate. Now, you all know that for the primary kind of amine, SN2 reaction is very good. But if you have R groups, there is an increasing rate of reactions if you start more and more substituting. Why? We shall see it very shortly. Okay. So even if you have a secondary amine, the reaction holds very good. In both the cases, it is fine. But E2 also, for a tertiary carbon, to the reaction proceeds faster. Now, you might see here, for this case, how E2 reaction with respect to order of the reactivity, how it increases by increasing alkyl substitution. This, how can you account is, as compared to SN2, is transition state stability. So you know that bond like formation and cleaving should happen at same time, unlike SN1. So if you look at E2 reaction in the transition state, you see double bond is partially formed, and the increasing of the stability with respect to double bonds, if you have more alkyl substitutions, okay, if you have from here carbon, this carbon, and here if you have more alkyl carbon, you will be having more of, it can stabilize the double bond. So once it stabilizes the double bond, the activation energy reduces, which promotes the rate of the reaction, which makes the reaction quicker. Okay? So as compared to only hydrogen you have here, like secondary amine or primary amine, what happens is one hydrogen, one methyl, or both hydrogens, this will not very well stabilize the double bond. Okay, so that is very important with respect to the reactivity. Means even if you have a tertiary carbon, unlike SN2, E2 will proceed faster. Also, you can see here, you have primary alkyl halide versus tertiary alkyl halide. In this case, because of you can see, if you have more number of R group, you get more substituted kind of structures or more stable kind of E2 products. Okay, especially if you look at the reaction below, what we are giving for primary versus secondary one, when you have a di substituted alkene, it is more stable like this as compared to a mono substituted alkene. You can see here, like if you take methyl propane, which is bromo substituted here, and when you bring in the alkoxide, okay, now you see as compared to here, you are having a lot of proton to primary amine, you are having a tertiary amine, so that you have a di substituted like CH3, C double bond CH2, then CH3. So the di substituted alkane is more stable because these methyl groups will stabilize the double bond. Also, let us elaborate more with respect to E2 mechanism for a system like this, like a tertiary carbon. So carbon attached to methyl, ethyl, and also a methyl group along with the bromine group. If you bring an alkoxide, like what you have seen in the previous case, like this, okay, what happens? You get a minor product and a major product, which essentially is a di substituted versus mono substituted, which takes us to an important topic, what is called as regioselectivity. What is regioselectivity? Which also brings us to an important topic, what is called as ZZEF. Okay, this is called ZZEF products. Okay, what are those? We shall see. So you should pronounce it as ZZEF. Okay, I am pretty sure from your language class which country this person and all can be rationalized from the name. And you all understood by now how alkyl halides will undergo dehydrohalogenations. Means how you remove hydrogen and halogen to make a double bond. Then you have alkyl halides with two or more beta carbons. Whatever you have seen now is only one beta carbon. Now, if you have multiple beta carbons, for example, you can see at this place this is halogen attached, so this is alpha. This can be beta, or here it can be beta. Okay, and also you have one more within the carbon, like carbon attached to one more methyl group. So that is the next substitute, like a beta carbon. In this case, you will have a di substituted alkene. So a hydrogen from here and iodine both will cleave to form a di substituted alkene. The more the substitution we get, the stability is more. So such phenomena is called ZZEF rule. So you can see here, you are having this is the carbon attached to iodine, is alpha, carbon, carbon, hydrogen. So we will have one hydrogen as beta hydrogen, and carbon bonded to next carbon system with one more hydrogen, that is beta. This environment is same. So when you bring in a base to react with methyl cyclohexane bromo substituted or iodide substituted product, what we get is a di substituted alkene as given here. Okay. So this is referred as ZZEF rule. Now, what is ZZEF rule and what are its implications? If you look at ZZEF rule, we are having beta elimination, especially when we have the major product which is more substituted double bonds. And we also talk about what is called as regioselectivity. And what brings us to a term called constitutional isomers. Okay. For example, you see here bromomethylbutane, four carbon entities. If you have one methyl, and as I told, in our case, you can have this is alpha carbon, this can be beta carbon, this is beta carbon, this is beta carbon. Again, these two are in same environment, so it is beta 1. This is you are having ethyl group, so beta 2. What happens if beta 1 hydrogens are gone? Means hydrogen from here and one bromine from here, or hydrogen from here, bromine from here. We get this is the transition state. So what happens is the hydroxide ion will react with it, takes away the proton, and the rest of the base will remove the bromide, and we get removing hydrogen from these two groups, we get a lesser yield minor product. But you want to remove hydrogen from here so that you will get a double bond here. So it is CH3, CH3, CHC, double bond, CH. Okay, so when you have a tri-substituted alkene, we get a major product. You can see here how well the double bond is stabilized as compared to here. Okay, as I told, if you have more substitution, the double bonds are more stable. Okay, so remember all the time, we can talk about regioselectivity and all those things. Regioselectivity means with respect to position. You can tell whether it is positioned in second carbon or in the first carbon. Okay, so removal from this part of hydrogens are tedious as compared to this hydrogen. So where regioselectivity plays an important outcome. So you may also look at even stereoisomers, especially how these phenyl groups are oriented, like preference of one over other. Especially if you remove, till now you are not seeing for double bonded system or something like that how a system works, but now you can see for a bromophenyl benzene. So you have diphenyl, you want to remove one hydrogen and one bromine, okay, in terms of sodium methoxide. What we get is obviously one hydrogen from here, one hydrogen or bromine from here, if it goes, we get a trans product. And keeping both phenyl groups in the same side of or the same side of carbon, we get very less yield. So which brings us towards stereoselectivity, regioselective, stereoselective. What is regioselective? Especially here, you can see it won't displace protons from here, rather it displaces proton from here. Even though you have beta hydrogens, that is regioselectivity. It is specific towards creating position isomers. Here it is specific towards creating stereoisomers. Okay, how phenyl groups are oriented. Still, you are talking about cis and trans. Okay, so that is the beauty of E2 kind of reactions, where regioselectivity at the same time stereoselectivity are of high priority. Okay. Now, let us see what are the properties of how we can.
Sir, sorry
Yeah.
for the interruption.
Yes. Yes. Yeah.
Sir, do we take the full units or recap the full thing for new students, new joiners?
Yeah. Can you again tell me once again? Can I?
Sir, So we keep separate class for the new joiners, like special classes.
No, new students, I asked them. See, it all depends on them. I asked Surya and Manish also.
So
If you want, I can take it. It's not a problem. You can just tell me the time. I can brief out. You see, the thing is, if I tell topic by topic, it is so tedious, and also at the same time, new students might not be like if they go through the material. If you have specifically doubts, like for example, I have doubts with respect to elimination reaction, then particularly we can discuss. If they come up with a topic what they have which they feel it is important, then it is very easier to discuss. Okay, at that time others also can join. It's not that only they can join, and it's not only for them. If others have any clarifications, I don't get this particular topic, okay, in 1 hour class or something like that, later also I can take in the evenings, or probably if you don't have any class that day, you can tell me the time. I can take for an hour, or so that some 2 3 topics we can effectively discuss.
thanks, sir.
Is that,
Thanks.
yeah,
Okay.
is that fine, Hariharan?
Yeah, sir. Yeah, sir. I will tell.
Yeah, so that's what. So whoever are feeling that a topic for them needs to be discussed, if you two or three friends, if you feel that it needs to be again discussed, please let me know. We can uh, discuss elaborately, and of course new students, when they are discussing, others too can join, no problem at all. But before that, look the handout, look the syllabus, particularly pick the topic. See, for example, if I'm teaching crystal field theory, others might feel already, yo, I know already. Even if I'm teaching elimination, some people feel already we knew. What is the extra part we are learning? If you come with that point, all might not attend. Whoever they are interested, they can attend, and they can ask doubts at that moment. Yeah, is that fine, Hariharan?
Yeah, sir. Fine, sir.
Okay. Yeah, and again, like Surya, Manish, and others who join late, they may go through the handouts and look into the syllabus, come up with any doubts or clarifications, lab or theory, anything. Yeah? Okay. Now, what we were looking at, or if you want to look for a take home message or like that, with respect to E2 reactions, is it's a second order reaction, a single step where the nucleophile entry and the bond cleaving is happening at the same time in the transient state. And we can observe the rate of the reaction, unlike SN2, for a tertiary carbon, it is very good as compared to a primary carbon, because we are stabilizing the double bonds if we have more substitution. And as you have seen for SN2, it is favored by strong bases. Now you can understand what is the difference between SN2 and E2. Till the transient state, everything is same. After that, whether to eliminate or to protect or to substitute, that depends on the last step. Okay? So if you have like this methyl group, it will go for substitution. If it has uh, like a dialkyl group, then it will think whether I should go elimination or I should go for substitution. And if you have tertiary group, definitely SN2 won't work. It is only elimination. So leaving group, if you have a better leaving group, faster is the reaction. And already we have discussed yesterday, if you have polar aprotic solvents, which improves the transient state, stabilizes the transient state, it will be more favored. So these are the important properties of elimination to bimolecular reactions. Let us see a tertiary group, like for example, E1 kind of mechanisms. If you look at this dehydrohalonization reaction, instead of base hydroxide group, take water. Then what happens? We get a double bonded. system here also. We are eliminating chlorine along with uh, like one hydrogen from one methyl group, so that we get a double bonded system. So this kind of thing is referred as elimination. So even if you take 1 ml water, 100 ml water, how much it can replace one hydrogen and one chlorine, that much only it will undergo. So it is a unimolecular, where the rate is dependent on first order kinetics, only on this concentration, not on water. If you look more carefully, the elimination reactions, it occurs unlike even a two-step mechanism, same like SN1. So what happens is carbocation. Once carbocation forms, the leaving group, when it departs, you get a double bonded system. Okay, so let us see how it goes. Again, we have the carbocation formation is the slow step. Once the carbocation formed, uh, the nucleophile entry or the base entry, and then double bond formation, leaving group exit. So these all occur simultaneously. Now you can see this is the mechanism. You have this chlorine you want to eliminate along with one hydrogen from here. So remove chlorine. You can see this is the positive charge you get here, because displacement towards chlorine electron density. So this is partial positive. And because of inductive effect, this carbon will become more positive, and the terminal or acidic hydrogen or beta part of hydrogen, beta part of carbon, where you have hydrogen, will be bonded to water. Then you get very quickly a double bonded system. So leaving group is chlorine departure, hydrogen departure, and the double bond formation uh, is happening at the same time. So that is the reason. And also, how much ever you take the water, it doesn't affect the reaction. So it is a unimolecular reaction of alkyl halide. So you can see till here, same like SN1. Okay, carbocation form. Okay, as soon as this to undergo to a double bonded system, there is a competition. Okay, so that makes same like SN1 and E1 reactions. You can see how the rate increases. If you have a tertiary carbon, the rate is faster. Now you might be getting doubt. In the E2 reaction also, I had said tertiary carbons are better. But E1 mechanisms also, tertiary like carbons are better. But if you have strong base, then you get E2 reaction. If you have weak base, water or alcohol, then we get E1 reactions. You see how we can construct it very beautifully. We told it is similar to SN1, SN2. Then now we are telling, in both the cases, tertiary is very fast. But if you have water, it goes even. If you have sodium hydroxide, it goes E2 reactions. Okay, so see how important, or if you look at the base itself, how to identify whether it is what kind of reaction. Okay. So we will make a short key points from this, and same like E2, E1 also is regioselective, where you make a more stable or a substituted end product. Okay, so here also Setzef rule will apply. So you can see here, if you take cyclopentane, pentane as compared to a hexane system, if you put water, again here also, this is alpha carbon, this is carbon, carbon, three hydrogens, but here carbon attached to one hydrogen. Whether hydrogen and bromine will go from here, or hydrogen will be eliminated from here or here. which means it won't eliminate from here or here hydrogen. It will remove from hydrogen from here, where we get a di substituted product. Okay? So same like E2 kind of reaction mechanisms. So you are applying Setzer rule. The important take home message is it follows first order kinetics. It's a two-step process where carbocation formation, then reaction with uh, double bond formation and leaving group. The rate of the reaction is more towards a tertiary as compared to a primary, but weaker bases will favor the reaction. And of course, these two are same. How the leaving groups, we have a better leaving group, the faster is the reaction. And polar protic solvents which can solvate the ionic intermediates, because please remember we are having now a carbocation, so they should be moving around to find out how to depart or how to remove an hydrogen and then to form a double bond. So as much as solvation we get, that much the reaction will be faster. Now, as already we had discussed, if you look from E1 and E2 mechanisms, in both the cases we see bond breaking and bond forming. Okay, hydrogen halogen removal and double bond formation. Only difference is the timing. Of course, base also is an important point. If you have E1 reaction, the leaving group comes off before proton is removed. You already knew that. Um, Whereas in the case of E2, we get a carbocation so that it becomes a proton so that easily it can depart. But in the case of E1 reaction, you have a transient state, okay, where both OH and the proton are there. Like any time it can react, and the halogen will go. Then we can have the timing wise it is different. And in E2 reaction, the leaving group comes off as a beta proton. Okay, already we have taken several examples with this, and then it occurs in one step. Okay, only thing in the case of E1 is we see carbocation, then reaction with nucleophile, then removal. That is the difference between E1 and E2 with respect to proton removal. Now, as already, if you compare with SN1, SN2 and all those categories, how to identify whether it is E1 or E2? First and foremost is look for the strength of base. If you give water, it will be E1. If you give sodium alkoxide or like that, E2 reaction. So stronger base E2, weaker base will E1 mechanism. If you give only ethanol, E1. If you give sodium ethoxide, potassium ethoxide, E2. Now, let us conclude, and before I go to the attendance and your a small question or problem, we should understand how E2 mechanisms, which are more common and useful, they are favored by negatively charged bases, alkoxide or base, sodium hydroxide. The reactivity occurs highest for alkyl tertiary group, followed by secondary and primary. In E1 mechanism, these are less because as compared to SN1 and E2 products. Because E2 reaction, E1 reaction can also have SN1 mixtures also sometimes, whether to elimination or to undergo substitution. Here also as compared to even mechanisms, we can see we need to have a weaker or a milder base, like it is not ionized. You won't see even mechanism happening at all for a primary alkyl halide, because primary alkyl halide you don't see any stable carbocation. So that is the driving force for E1 versus E2 comparisons. Okay, so this is all about E1 and E2, and what are the parallels with respect to SN1 or E1, what we just now discussed in the last point. So as I told you earlier, SN1 and E1 will have same carbocation formation. In the case of SN1, we see a nucleophile coming, so we get SN1 reaction. Intermediate is same, but here how the base attracts the beta proton, you get whether it can go SN1 or E1. In that case, if you look at SN1 reaction, the nucleophile, it attacks the carbocation, whereas in the E1 you are removing a base, so that you get a double bond, which essentially takes us to a final point saying that E1 reaction, it often occurs with SN1 competition. So that is the reason why E2 reactions are very much useful as compared to E1, because whenever you say I have done E1 reaction, always there is a, it can have both the species, like a, because essentially strong base here also. Okay, the nucleophile will determine how it really reacts, because in the case of substitute SN1, you can also do the reaction with water or alcohol. Here also you can do the same thing, but that is the reason E2 are more like applied or being used. So let us see how can we predict whether the reaction, what kind of reaction it undergoes. If you have good nucleophiles, which are weaker bases, okay, so good nucleophiles, weaker bases, they favor substitution over elimination. Whether you want to get a doubt whether it will undergo elimination or substitution. So if you have good nucleophile, weaker base, eliminations. So for example, iodide, bromide, cyano group, acetate group. So if you see this, definitely you can replace bromide with iodide, and then because it's a weak base, no elimination reaction happens. If you have bulky non-nucleophilic bases, what happens? You can see substitution reactions. It won't allow substitution reactions because of steric hindrance. You can see potassium ethoxide or like tetrabutaoxide, because of, as compared to ethoxide, if you take tetrabutaoxide, you get eliminated the product rather than the substituted one. Tertiary butanol is formed because you cannot have tertiary butyl group, which makes lot of steric hindrance. So here elimination is formed over substitution reactions. So in conclusion, to sum up, we have competition between E1, SN1, E2, SN2, and Sedzef rule, how it favors, which essentially tells conjugation is more preferred. Disubstitution or trisubstitution is more preferred. So these are the comparisons between E1 and E2. Now I want all of you, before I close the class, You may tell your attendance. 101 Rakesh.
Present, sir.
And I want you to tell me A to D, which are SN1, E1, SN2, and so on. Go through this, identify and tell me which is SN1, SN2, and so on. Ileraj, Ileraj, are you there?
Yes, sir.
You may,
Present.
yeah, you can tell the answer for this reaction tomorrow also. Yeah. And
Okay.
Shashank, 3,
Sir, 3 is Tarun Raj, right?
3 is
Sir,
Sir,
3
he
is
had
Tarun
power
Raj.
cut, sir.
okay, no
Yeah,
problem, no
yes, sir.
problem. Yeah, okay, no problem.
Shashank
Shashank,
present, sir.
okay, fine, fine, Shashank. Yeah, Tarun,
Yes, sir.
Tarun is present, right? Harish,
Present, sir.
Srinivasan Reddy,
Present, sir.
Satvika,
Present, sir.
Amitoj,
Present, sir.
Ayyappa Reddy,
Sir, Ayyappa Reddy present, sir.
yes, yes, Sridharan,
Present, sir.
Ramchandra Rao,
Present, sir.
Anurag,
Present, sir.
Shubh Verma,
Present, sir.
Karthik,
Present, sir.
Shaz, Shaz, I saw him.
Present, sir. Present.
Okay, fine, yeah. Hariharan
Present, sir.
and Surya,
Present, sir.
Sai Kumar, even I, yeah, okay, fine, 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 fine. Uma Venkat Reddy, Rudresh,
Sir, Umang Reddy present, sir.
okay, okay, yeah. Yeah, Karthik, any doubt? Okay, yeah. How about Yash, Uday, and Surya, Manish? Others.
Yeah,
Present.
sir.
Sir, present, sir. Present, sir.
Oh,
Present,
oh,
sir.
fine, fine, fine. Yeah, fine. Yeah.
Thank you,
So,
sir.
yeah, I think someone raised the hand. I don't know why. Okay. So others, once you are done, you can leave. Okay, you are done with attendance, and I think all of you are present.